Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and today in the Masterstroke series I am going to discuss about the chapter Electromagnetic Wave. Now you know that this is the smallest chapter in your both combined PU1 and PU2, but from this chapter, if you see this video, at least one question definitely you can answer if you just watch this video, which will be hardly 15 minutes long, and one question guaranteed. If you watch longer videos of your PU1 section, even though there are a lot of things are there, but you will not be able to answer one question. Maybe you can answer, maybe you are not, but the coverage was big, question number was less from your PU1. So this is a chapter where one question up to two question comes sometimes. So we will see what are the important concept in this chapter. So first, obviously, displacement current, then we have speed of light, and we have electromagnetic waves, electromagnetic spectrum, etc. So very small main three concepts. Other than that, there are a few more concepts. So first we will look into the concept of displacement current. So the changing magnetic field can induce an electric current, but this is not the only cause. Also, the time rate of change of electric field can also be a reason. The current produced by a changing electric field is called displacement current. Now in a circuit, there are two types of current. One is called conduction current, one is called displacement current. This is displacement current. What is a conduction current? If you have a conductor, if this conductor is carrying some current, then this is called a conduction current. Okay, there is a conductor which is carrying some current. This is called conduction current. The total current I is the sum of the conduction current denoted by IC and the displacement current denoted by ID. Now where do we see displacement current? The example that is given in your book is the capacitor one. Suppose we have a parallel plate capacitor. Okay, the capacitor is being charged by some battery. Okay, what is happening is that the current is flowing through here, but in between the capacitor plates there is no conductor. So apparently the conduction current, which conducts only through a conductor, cannot pass through the capacitor plate. So what is happening inside this capacitor plate? The electric field is changing, and that changing electric field gives rise to ID. Now in any other cases where you somehow, if you can combine these two factors, then IC and ID will be, total current will be IC plus ID. Now in this case, outside the capacitor plate, ID is equals to 0 because electric field is constant. Inside the capacitor plate, IC is equals to 0. So inside the capacitor place there is no conductor available, so conduction current is 0. So only thing that exists is ID. Outside the capacitor place only IC is there, ID is 0. So total current generally is given by IC plus ID if both can exist simultaneously. In some cases, if you are having some changing electric field linked with the conductor, there will be conduction current, there will be displacement current. So in that case, I will be IC plus ID. This is the general formula. Now the expression for ID is given by d phi E by dt into epsilon naught, similar to that of magnetic field. If you remember, the formula was similar. Okay, d phi B by dt was induced EMF. From there you can calculate the current based on the resistance. Here they are saying the direct formula is, this is for current. Okay, this is called displacement current. This term is called displacement current. This is ID. Okay, now let's move on to Maxwell's equation. So these are the Maxwell's equation, 4 equations. Even though it is not directly developed by Maxwell, okay, Maxwell contributed only in this relation, that is Ampere's Maxwell relation or corrected Ampere's law. Okay, in Ampere's law, the formula given by B dot dl is equal to mu naught into I. But Maxwell said that I is not only I, it consists of two components. One is IC, another one is ID. So he modified this equation as B dot dl equals to mu naught IC plus mu naught epsilon naught d phi E by dt. So this question came in your PU exam. What is the equation? So you have to remember that Maxwell's equation or Ampere Maxwell equation has mu naught epsilon naught both here, whereas displacement current is only this much. This is displacement current, okay? But when you are writing the entire equation, you have to include mu naught as well. Now this is Gauss's law of electromagnetism, this is Gauss's law of magnetism, this is Faraday's law of electromagnetic induction, and this is the Faraday-Lenz law actually, and this is the Ampere-Maxwell law. Now when you combine these four equations, you don't need to remember everything, only this equation is important, okay? When you combine all these four laws together and try to solve, try to find a general solution, the general solution was very, very interesting, okay? So when you solve these equations, then you get something called a electromagnetic wave, okay? So electric field and magnetic field, they are not separate quantities, they are linked with each other. You can link them because electric field is here, magnetic flask is here, so there are all types of relationship is here, and through that you can basically link electric field and magnetic field, okay? Here as you can see, magnetic field is here and electric flask is here. So electric field and magnetic field, they are not separate quantities, they are linked with each other, and if you solve them, a general solution gives you the process is little complicated. If you study physics in future, you will know how to solve these equations, okay? And the general solution gives you the electromagnetic wave, okay? And also the wave that how do we know that is an electromagnetic wave? Because you get a wave equation, and the speed of that wave equation turns out to be c equals to 1 by mu epsilon naught mu naught, okay? If you put this value of epsilon naught mu naught, you will get this value to be 2.999 into 10 to the power of 8 meter per second, which is the speed of light, okay? So the wave, that equation, the equation is not, there was no direct proof that this is the electromagnetic light is electromagnetic wave. Only fact is that once we solve the equation, we get a wave equation. That wave moves with the speed of this, which is very very close to approximate value, actual value. It is matching with the exact value of the speed of light. So then we can say, okay, this is moving with speed of light, means light must following this kind of wave, light is this kind of wave. Then the science progressed from there on, okay? Till that point light was wave, it is fine, but what type of wave was not clear. So now we know light is a electromagnetic wave. There is another equation, E by B or E naught by B naught, we will see that in a while. So before we go there, you have to remember that we have launched Abhyas KCET test series, where you are getting total 35 tests. Out of that 4 are free and 31 paid. In this test series you will get fully solved solution of the question papers discussed and solved by us, and chapter wise one short revision videos also you will get. You will get chapter wise insight for last 5 years KCET question papers. Live doubt solving will be there. So if you are still in doubt, you have to purchase the Abhyas test series for 1498, right? And you can crack the KCET with top rank if you just practice more. So this is the opportunity to practice for yourself for getting a better rank in the KCET exam, right? Now let's move on. Electromagnetic waves. Let's see. An accelerated charge is a source of electromagnetic wave. Okay, so static charge cannot produce electromagnetic wave. Electromagnetic wave can be produced only by an accelerating charge. Okay, an accelerating charge produces mutually perpendicular electric and magnetic field that varies with time. It's very, very important that both electric and magnetic field should vary with time, right? Electromagnetic induction d phi b by dt, and electric field displacement current d phi e by dt. So both has to change with time. So time varying electric and magnetic field both are required for successful production of electromagnetic wave. So if they give you a question, MCQ question, question. Most of the MCQs from this chapter are easy. Okay, if they give you a question, which of the following is necessary for producing electromagnetic field? Only time varying electric field and static magnetic field. Time varying magnetic field, static electric field. Both time varying electric and magnetic field, both static electric and magnetic field. So necessary condition is both has to be time varying, both has to change with time. If any one of them is constant, there will be no electromagnetic waves. Okay, clear? Now you can see that this is the why I am saying both has to vary. So electric field is varying like this, magnetic field is varying like this, and that together is the process of the producing electromagnetic wave. The general direction is basically the electromagnetic wave will propagate in the mutual perpendicular direction of electric and magnetic field. Now equation of the electromagnetic wave that we are talking about, so electric field and magnetic field both are time varying, both are propagating. So electric field is E naught sine kz minus omega t, and By is equal to sine kz omega t. So this is changing along x direction and this is changing along y direction, but the common direction of propagation is both along the z direction. Okay, so it is propagating along z direction, but it is varying. The component is along x direction. This is varying along x direction. This is varying along y direction. Common direction of propagation is z direction. This is a simplified wave equation, not the exact wave equation. Exact wave equation is little complicated, but you can understand that. Here K is related to the wavelength lambda of the wave by the usual formula. This is not L, this is lambda, okay, of the wave equation. K is equal to omega by C, also given by 2 pi by lambda. So this is a wave relation. This is not directly related to electromagnetic wave. This is common wave equation, first PU class. Okay, so if you forgot that relationship, you can remember it from here, omega by C and 2 pi by lambda. Next, what? The wave propagates in the direction of E cross B. So obviously, as I said, the wave is basically perpendicular to both electric and magnetic field. So this is the this is how it is propagating. And one more thing is that speed of light, this is speed of light is E naught by B naught, okay, either Ex by Bx, so sin kz will cancel, or you can write E naught by B naught. This is also very, very important. So speed of light is magnitude, amplitude of electric field divided by amplitude of magnetic field. Okay, let's see one question from KCET. This is a question directly from KCET. The ratio of magnitudes of electric field to the magnetic field of an electromagnetic wave is in the order of, very simple, very easy question. So electric field to the magnetic field, electric field to the magnetic field, and that order is, that value is exactly 3 into 10 to the power of 8 approximately, right? So we can say that this is of the order of 10 to the power of 8 meter per second, right? We can say that if you ignore these 3, so of the order of means the highest 10 to the power, right? So obviously it is 10 to the power of 8 meter per second, okay, meter per second. If they give you the reverse order, if they give you the reverse order, that is B naught by E naught, then it will be 10 to the power of minus 8 meter inverse second. Okay, because it is opposite to that of this, so you have to remember that unit will also reverse. This is a question which is already came. This question might come, so you have to be careful. If they say B naught by E naught, then not only 10 to the power will become minus, the unit will also reverse. Okay, so there will be 10 to the power of minus 8 meter per second, 10 to the power of 8 meter inverse second, 10 to the power 8 meter per second, 10 to the power 8 meter inverse second. So you have to identify that, because they have asked me to find magnetic field by electric field. In that case, the order will be 10 to the power of minus 8 and unit will also reverse. Okay. Now this is the electromagnetic spectrum, the famous electromagnetic spectrum. You have to remember that the rays which start at the top, they have very high frequency and very low wavelength. So wavelength is small but frequency is very, very high. So you can see that frequency is of the order of 10 to the power of 23, whereas wavelength is of the order of 10 to the power of minus 14, and this zone is called gamma ray. Gamma rays have highest frequency, lowest wavelength. Okay, next in the thing is X-ray. X-rays are in between gamma rays, as they have smaller frequencies than gamma rays and smaller wavelength than gamma rays, but everything is more compared to ultraviolet rays. Okay, for example, frequency is more for X-rays than ultraviolet, wavelength is less compared to ultraviolet. Ultraviolet ray coming in between, just before our visible range, it has a higher frequency than our visible range and lower wavelength than our visible range. Now visible is obviously the 7 colors that we can see. Okay, violet, blue, green, yellow, orange and red. Okay, so this is the approximate wavelength range. You don't need to remember the values exactly, but if you remember the order, sometimes it helps. Okay, so gamma, X, ultra, visible, infra, micro, radio. Okay, so this is the order. In between short radio, television radio, AM radio, long radio, you don't need to remember, but you have to remember gamma, X-ray, ultra, visible, infra, micro, radio. Okay, if you remember this order, it will be very, very helpful for you. Now infrared, which comes below the visible range, okay, it has higher wavelength, lower frequency. Then microwaves. Microwaves is the same that is used in your kitchen. If you ask your mother, or if you know how to use the microwave for warming your food, so that is basically same thing. And microwaves frequency matches with the frequency of natural vibration of water. Okay, water molecule. So basically what happens is that a microwave can excite water present inside our food. So microwave can resonate with the water, and it can transfer the energy only to water molecules, nothing else. If you just put any glass item or steel item or anything, any plastic item, it will not absorb anything from the microwave. Only the water present inside, that will only absorb the heat from the microwave, and that all our foods are basically contains water. So water is getting heated up, that water is transferring the heat to all the other food items, all the other chemicals present in nearby it. So that's how it can heat up the food. Okay, so microwaves is one of the very common application of electromagnetic waves, and microwaves are also used in radar system. If you know, radio waves are very common. If you listen to FM radio or AM radio or any other type of radio, obviously your favorite channel, let me know in the comment below what is your favorite channel, and from there you can that is basically radio waves. Okay, and based on the requirement, it can transfer energy for a very long distance. That's why radios is very popular. It was very popular. It was one of the most common channel of transferring news, media, everything. Okay, before television era, when there was no television, people used to rely on radios, because radio towers can transmit sound or sound, not sound actually, it is a modulated kind of energy. Modulation is not part of the syllabus, but you should remember that radio waves can transfer information at a very long distance. Okay, even observing very distant star, we rely on radio waves. Okay, now there are few examples, and their wavelength range is given. So radio has the highest wavelength, smallest frequency. Okay, rapid acceleration and deceleration of electrons in aerials, receivers aerials. Okay, there are different production and receiver detection is given. Okay, but it is not super important. This is important, what I felt. Infrared comes 1 millimeter to 700 nanometer, light is 700 nanometer to 400 nanometer, ultraviolet is 400 nanometer to 1 nanometer, whereas X-ray is 1 nanometer to 10 to the power of 3 nanometer. Anything less than 10 to the power of minus 3 comes under gamma rays. Gamma rays are very gamma rays, X-rays, in fact ultraviolet ray, they are all very harmful for our bodies. We know that some of them are getting absorbed in our ozone layer. Okay, ultraviolet, specifically ultraviolet rays which is coming from stars, that is getting absorbed in the ozone layer, right? So there are few ways how they can be produced and how they can be detected. Not super important, but wavelength range and this smaller table it will help you to remember question. Let's see one question from this chapter, from KCET question paper. Which of the following radiation of electromagnetic wave has the highest wavelength? So highest wavelength amongst the given list. Okay, it is not the highest wavelength. We know that radio wave has the highest wavelength and gamma ray has the smallest wavelength, that we know. But here, is there any radio waves? Radio wave is not there. So who is next after radio? And after radio, microwave is the next. So microwave has the highest wavelength from this given table. So obviously microwave we will tick. Okay, so this is it. This is a chapter from where you can answer one question up to 2 questions. So we will conclude this chapter, and if you are watching this video for the first time, don't forget to subscribe to our channel. A lot more things is happening in our channel, and also subscribe to Abhyas test series if you have not yet done so. I'll be back with a new lecture soon. Till then, bye.